Hello there, Khaled El Malawani here. So today we'll be talking a bit more about the MPU 6050 here, namely about extracting the degrees of rotation from the gyroscope. As you might have noticed and mentioned in the previous video, the MPU 6050 produces a data of degrees per second. It is important to be able to convert it to degrees for most applications, especially if you want to account for the rotation of the robot towards, of course, the right or the left. And we'll get started with the Arduino code here. So in this code here, we are going to determine how to extract the degrees from the gyroscope using three different methods. The first of all, we set up the connections between the MPU 6050 and the Arduino. So we need to call these libraries here. These are the exact same way it is set up on the MPU 6050 code that was mentioned in the previous video. And as we move on with this here, we can notice that we first of all initialize and calibrate the gyro. Notice how we're not calibrating the accelerometer because we'll not be using it in this code. And then of course we print the various commands or the various inputs here just to make sure that we are aware of what is currently going on with the code. Now, an important remark here is this is how we're defining all three methods. So to pretty much to determine the method you're going to use, you can just uncomment the one you want, and this method will be the one demonstrated in this case. So there's the first method employs the millis function, which we'll see in a few minutes here, as well as the micros function, and finally the sample rate. Now, an important thing to note is when do I use which, right? So we can talk a bit more about details in a second here, but the first thing to mention is the first important thing to mention is when you want to account for overflow. So how long basically you're going to use this? So the millis function overflows in about 50 days. So if you use the robot for more than 50 days, you cannot use the millis function. But anything less, then you can use it. However, the micros function does overflow after about 70 minutes. So, okay, so you cannot use it more than 70 minutes. Finally, the sample rate does not overflow. It's just a simple mathematical operation, as we'll talk to in a few seconds here. The first one is the millis function. But before we get to that, we should first note that we do extract the gyro data and we divide it by 131, which is the value demonstrated in the documentation, to be able to extract the data into degrees per second. So first method we're going to use here is the degree method using millis. In this case here, we do need a few global variables. The global variables are the same for both the millis and the micros. The millis function will go need a Boolean flag. This will allow us to only run the code after the first loop is completed, and we'll get to why that is necessary in the code below, as well as the previous time, which just holds as the name implies, the previous time of the millis or the micros, depending on the method you're using, that was stored previously. And finally, if we are or if we are using the sample rate method, then we'll just need to have the sample rate defined. Okay, now one more thing to mention, the setup function here is we do assign the false variable to the micros and millis methods. This is important because we'll see that in just a few minutes again. And then first thing we do is we extract the gyro, as I mentioned, and then in here, we say that if the is-for loop complete is true. So that means if you did complete the first loop, then we're going to run the code inside here, which all it does is it creates a variable and initializes it to millis minus the previous time, which accounts the time for one loop, which makes sense. So millis will get the current time that has passed in millisecond since the robot has started. And if you subtract that from the previous time, then you have the time for one loop. Using the time here, the time is in milliseconds. So that means that you need to divide it by 1,000 because there is 1,000 milliseconds in 1 second. So this will ensure here that your units will be in seconds, and the gyro data is in degree per second times the seconds. The seconds will cancel out, and you're left with degrees. Now we plus equal it. That means we increment it with the previous value, because that will make sure that if I rotate the robot, it just keeps the same degree. So if you just had an equal sign, then it would reset and it would just be the value of the basically the degree at the current moment, and you cannot really determine how much degrees has passed. And then this is the important part here. So the previous time is equal to millis. So what this does is it stores previous time to the value of the current millisecond, which is after the if statement. And then finally, we have this statement that will only occur once, which is if the first loop is false, then you will change it to true. This one here has to be after the previous time is equal to millis, which has to be after the if statement. This is the proper order you have to put it. You cannot put a different order. It will not be accurate. Okay, or it will give you error depending on how you change it. So we have this here. Now, if we plug in the robot here and we upload the code onto the robot, we can see the accuracy of it. I should mention that the method using macros is the most accurate, but we'll see that throughout the video. So we can just upload the code here. And first thing it's going to do is, of course, it's going to set up and calibrate the MPU6050. Okay. Okay, let's try again. Perfect. So it is done uploading here. Then we can just open the serial monitor and it will calibrate the MPU6050. And as you can see here, we have the gyro degree is printed out. If we just scroll down to the code, you'll see where it is printed out. Where do we call the print command? And then there is error. Now, all of them will produce error. This is something common with any device you're using when it has noise. However, as you can see here, the error seems to be quite insignificant at the 0.01 scale. If you really want to, you can remove the error that is produced over a certain amount of time. So you can use a counter, and after, let's say, 1,000 inputs of the counter, then you can just remove, let's say, 0.05 of the gyro degree. And that is one way, or you can even create a digital filter, which just means if the gyro Z, which is the input extractor from the data here, you can just allow some variables to update and some not. However, I would recommend that you just keep it as it is because the error is quite insignificant. But the one thing to note here is if I rotate this to about my robot here to about 90 degrees, it produces about 50 degrees. So it is inaccurate. And if I do the same thing and get it back to the middle, so this is the initial starting position, and get it to the other side, it's also about 50. If you notice, it's about the same in both sides. But the reason why it doesn't reach 90, even though I turn it to 80 degrees, is because the code is actually running faster than 1 millisecond. And we can show that by just inputting a function here, serial.print line, a new line, and we can just print the time for one loop. And we'll notice here, after the uploads, if the time for one loop is more than 0.5 of a millisecond, then it will round it to 1 millisecond. If it's less than 0.5, it will round it to 0. So in this case here, after it uploads, you'll see that the output, after it of course initializes the MPU6050, you'll see that the milliseconds is determined to either be 1 or 0. Now this is slightly confusing to read. Let's just comment this one out here. And open serial monitor again. Okay, so it's finished calibrating. And as you can see here, the time it takes to complete one loop is about 1 or 0 microsecond. It sometimes goes to 2, but it's about 1 to 0, milliseconds. Okay. So that's the reason why it's not the most accurate, because it cannot determine anything less than 1, basically. Okay, so we can comment this one out. And then we can see the microseconds here. We can actually start using this method, and we do that by commenting this one and uncommenting the method using micro. If we see the method using micro, it's the exact same thing. The only difference is that we're using micro instead of millis. And of course, we're dividing by a million because there is a million microseconds, in 1 second. Okay, so that is the two things that have changed. Other than that, it's identical to the millis method here. And we can just upload the code here. The first thing we're going to see is the time for one loop. Remember that this one is commented out. And we can just open the serial monitor for that. And we will see that it is about 600 when it completes. So as you can see here, if we just stop the auto scrolling, you'll see it's about 600, a bit above, a bit below. So it is less than basically 1 millisecond. It's almost about 0.5 actually microsecond. So as you can see here, this one, the microsecond is way more accurate if you want to use it in terms of its numbers here. But keep in mind that it will overflow after about 70 minutes. Okay, so we can comment this one out again and uncomment this one and upload it to the robot one more time. Okay, and it will just calibrate here. And then it still has errors. As I mentioned, they will all have errors. Now this one is less significant than the millis one. And we'll just rotate it to about 90 degrees here. And this is exactly almost about 90 degrees. And as you can see, it produces the same value. Now it is negative because recall that a clockwise rotation in the IMU produces a negative value. If we go back to the starting point and we go back to the other side here and go to 90, we will see it's also about 90. So the micros one is way more accurate than the millis, and as demonstrated here. Now, finally here, the third method we can talk about is the sample rate. Now, as I mentioned, the default sample rate is 8,000. And that is given certain conditions. The major condition is there's nothing else going on. Okay, so according to documentation here, it's 8,000 if there's nothing else going on. What I mean by also nothing else is even the conversion to 131 should not occur. Okay, so the idea is the 8,000 is if you just divide the value extracted here and divide by 8,000, it should be about correct. But if you do it that way, it will produce noise and it's not proper because this without the divided by 131, it does not produce the proper value. Okay, so the best way to actually determine this is actually using this method here. So using the micros, you can launch this code and then print the time for one loop, okay? And then run it on your code here and see how much time it takes. So you can even use an averaging function. So you collect the time for one loop over a certain amount of time, divided by basically the number of values you have in your array, and you will get an average. But let's just use 600 microsecond here. So we can just open our calculator and then go. So we know that it was around 600 microseconds. Let's get that into seconds. So we divide by a million, and that gives us 0.0006. And so that is the amount of seconds for one void loop. And now the sample rates is in units of hertz, and hertz is 1/second. So we can just divide 1 divided by 0.0006, which is the value just determined in seconds, and it will give us about 1,667. And so we can use that for the sample rate determined here. And after we do that, we can just divide it by the sample rate. Now remember, this method here will not overflow. You can run this for as much as you want, and it will keep going. It's also slightly easier to read. So it is basically a method. If you're working under 70 minutes, then it's basically a method of preference at that point. Okay, so we have that here, and we can just upload this code to the robot. And just open the serial monitor here, let it calibrate. So there is slight error again for the third time I mentioned that. So as if the error seems to be increasing quite rapidly, then your sample rate is not optimal. So you can play around a bit with that number here, maybe reduce it a bit, increase it a bit, but for the sake of this presentation, I won't do that. And if we just rotate it one more time here, this is about 90 degrees as well. And yeah, and that is very, very close as well. So as long as you did your math correctly, then you will be getting the proper values. One last thing to mention here is this is how we extract the degrees using the gyroscope. The MPU6050 here also has an accelerometer. However, it is important to note that the accelerometer is in units of G, which is about 9.8 meters per second squared. So you have to keep in mind several factors there that you will divide by, first of all, 9.8, and then of course divide by the constant determined in the documentation. And you will also have to time by the time twice. Okay, so that means that any error accumulated will accumulate by a factor of 2. Okay, so it's not only incremented by 2, it's multiplied by a factor of 2. So it is actually a thesis to be able to extract the distance using an accelerometer only without a magnetometer. So it's extremely hard to do. But if you want to get a look at it or even try it with your MPU6050 or any accelerometer, go ahead and try it and you will reach to that conclusion. If you do, you can try and improve it a bit more by putting filters or others. But yeah, so it's a fun project to look around, but it is also important to keep in mind. So that's it for that video, and I hope it was useful to you, and have fun in your Arduino adventure.